All right, good afternoon online. All ready? Cado, ready? Good afternoon online. You all here? Good afternoon, nice. All right, so today we want to continue from last day. Remember last day we did a lab. We did a lab on how to find specific heat capacity of water. And yeah, we did water and yeah, water. All right, so let's do a quick review on that, and then we're looking at something called specific latent heat, and that's it. All right, we're just doing one new thing today, and that's it, right? And that's some questions. All right, so as a quick review, we looked at a quantity called specific heat capacity, right? Which was the energy required, to change the temperature of a particular mass, right? And we said at any point in time, if you wanted to find the energy to change the temperature of a particular substance, particular mass of substance, we use this little formula here. That's okay? So this formula here is what we use to find the energy required or released during a temperature change. Right, during temperature change of a substance. All right, just make a note of that. So what you will notice is that we focus so far on temperature change. The next thing we're going to do is phase change. All right. So our next topic, our next quantity, our next thermal quantity is called latent heat. Okay. What's happening if you heat ice, Christian? It'll melt, right? So initially when it melts, what you have undergoing there is a phase change, right? We need to be able to find the energy for that phase change. Okay, so we're looking at latent heat, LH. All right, I'll give you a quick little definition there. Latent heat is the energy required, to change the state or phase of a particular mass of a substance. Something very important, without a change in temperature. Right, without a change in temperature. Right, formula looks like this. Latent heat is the energy required to change the mass, to change the phase of a particular mass. That's it. Right, so underneath that, I don't have the space, write the formula for latent heat. And it could also be written like this, right? E is equal to MLF. Sorry, MLH. Finish it? Right, Viraj, just make a little note of that new formula down there was latent heat, right? Energy required for temperature change, for phase change. I want to show you a quick little simulation of how we apply this. Right, please underline the part that there is no temperature change, right? There is no temperature change in latent heat, and in specific heat, there's no phase change. Right, just make a little note of that, right? Finish, right? Finish. It's just you send in the class or you're on your phone. Come on, which one now? Afternoon. All right, so what's your smallest simulation here? All right, I'm going to show you about the heat capacity. I don't know if I show you this simulation, right? So here we have two substances. This is a simulation for specific heater, not what we're doing. So this will cause a temperature change. So we are heating something at 20 degrees Celsius. One has a large heat capacity and one has a small heat capacity, right? Well, which one do you think will heat up faster? The one to the left or the one to the right? Which one do you think will heat up faster? The one to the left or the one to the right? The one with the small specific heat capacity or the large heat capacity? Huh? What y'all think? Anybody online? Which one? The one with the small? All right, let's see. Right, look at how fast the temperature changing on the one on the left. See that? The one with the small specific capacity heating up much faster. Okay, so that's the concept of specific heat capacity. The smaller the value, the faster you will undergo a temperature change. All right. Okay. Well, that was some last week before, right? Today, we want to take a look at latent heat. Right? So take a look at what happening here. So we have ice, right? We have the ice. Look at the graph of the ice. Right now, the ice is at minus 20 degrees Celsius. And I'm going to heat it. Look at the graph. Tell me what you notice when it started to hit zero. Right? What's staying constant? Temperature staying constant, right? And what happened to the ice? It melted. You recognize that? Right, and when it fully melted, then it underwent a temperature change. So that, let's redo it one more time. Watch it good. So you're heating and you're heating and then you're heating again. You keep heating it. As soon as it hits zero, it starts to melt. You're seeing now online, Karina? So it undergoing a what change there? Phase change, right? And now, as soon as it melts, it starts to undergo a temperature change. I'm going to let it keep heating. Online, you're seeing that? Everybody seeing it, right? Malini, you all seen it? All right, good. Shana message the host, right? Right, look at what's going to happen. You'll be heating it more. As soon as it hit 100, what's going on there? It's starter, not dissolve, what's the word? It's starting to evaporate, right? It's started, right? You'll start to vaporize, right? You'll see that? And everything happens at one temperature. See that temperature staying constant, and now it's changing into a gas. Right? So if you look here, excuse me. I'm sorry, all right, good. So you'll get some work done today. Right? So if you look here, this horizontal bar and this horizontal bar, it underwent a what type of change underwent there? Phase change, right? It underwent a phase change. Here's a phase change. So if I asked you to find the energy here and find the energy here, you will use E is equal to ml. Are you okay with that? Yeah? One thing I want you to pay attention to, when it going from solid to liquid, it'll be LF. When it going from liquid to vapor, it will be LV. All right? I kind of like this graph, so if you can just make a sketch of the graph now, please. Make a little sketch of this graph on the right-hand side here. Right here is the temperature change. So that graph on the right-hand side, right? Yeah.
Você demora professor, if that repeat next team, I got get some.
Cameron, you okay? Difference between phase change and temperature change, Maria? You're okay with the difference between phase change and temperature change? Cameron? Right, one thing you'll recognize while you're drawing, right? During a phase change, you'll recognize that the temperature staying constant, right? So copy this down and we're going to go into some numbers now, right? Some calculations. If you could probably write in the states, right? And let me see if I can write it in black here for you, right? So here is ice. Here is where it melts. Here is water. Here it is vapor. All right, number oil join cell. Right, for those who now join, remember the formula for temperature change, MC delta theta. Formula for phase change, MLH. Anybody writing online? All right. Right, let's get into some numbers here. All right, so first one, right? So we're doing some small calculations here, right? So I'll give you the mass of ice. Mass of ice is 5 grams. And the latent heat of fusion. Latent heat of fusion of ice is 3.3 by 10 to the power 5. 3.3 by 10 to the power 5 joules per kilogram. Right? Question 1. Hey, Malik. Question 1. We want to find the amount of energy required to melt 5 grams of ice. Right? So 5 grams of ice means that we're using, well, let me write it here for you, sorry. Right? They want you to find the energy. Find the energy required to melt the ice, right? So since it's a temperature, since it's a phase change, what's the formula we use in question? Right? E is equal to M, to be specific, MLF, right? Because it's fusion. Solid to liquid is fusion, right? Nice. What do we do with the mass? What do we do with the mass? The mass is 5 grams, right? Sahara, what do we do with the mass? Look at a little hint here, right? Sahara, what you'll do with the mass? Right? The mass is in grams. What do you do with the mass? Right? Correct, Maria. Did I see Sahara? Right, convert to kg. How you know? Jacob? You look at the unit for the latent heat. If it's kilograms, you're working in kilograms. If it's grams, you're working in. Right, so you'll end up with 5/1000 by 3.3 by 10 to the 5. How much is this? No, tell me what's the whole thing. Tell me the whole thing now. You want work. 1 point on the loss by a load. Okay, back next time.
I understand, but the robotic wasn't so when we went. I guess.
How much you got here? I got 1650. 1600. Check it back. I seen different answers. How much all you get? Right, the key word here is melt, yeah? So you'll know which formula to use, right? 1650. 1650 joules. Have a calculator. All right, let's try our next one. Sorry? Yeah, S8Cs. So I'll give you a specific capacity as well. Right. So this one a little bit different. We will do this one together again. I would like you to find, let's see if we can find the energy. Find the energy required to change ice from 0 degrees Celsius to water at 10 degrees Celsius. You'll see that? So the mass of ice is 10 grams. I gave you the specific capacity of water, 4.2 by 10 to the 3. And I also gave you the latent heat of fusion of ice. Right? I didn't write the unit. Sorry about that. I would like the energy required to change ice from 0 degrees to water at 10 degrees. All right, copy it down. Which one? 4.2 by 10 to the 3. All right, so we're gonna do this one together. Before we start the working, right? Let's see if we can show this in a graph. So we'll have an idea how we're doing this actual calculation, right? Right. So we're starting at 0 degrees. Here's 0 degrees, right? We're starting with ice at 0 degrees. When you heat the ice at 0 degrees, what will happen to it? What's the first thing that happens to the ice? It'll start to melt, right? So it will stay at 0 and it will melt. So all here is melting, right? And it will melt and become water, right? When you heat it further, what will happen? It's already water. What will happen to it? No, it wouldn't evaporate. Right. So, right, and when all the ice melts and is now water, it's water at 0 and you heat it, what will happen? Temperature will start to increase, right? So the temperature of the water will begin to increase until we reach, in this case, 10 degrees. That's okay? So if you look closely at that small diagram, it has 2 stages. A melting stage and a temperature change stage. So there's one stage here, and there's a next stage here. All right? So if I ask you to find the energy required to do the whole thing, what you'll do? The energy required will be the 2 of them, right? The energy during melting plus the energy during temperature change. Are you okay with that? So we have 2 separate things happening here for the ice to go from 0 degrees to water 10 degrees. Ricardo, you see that? So the ice at 0, it melts, we had to find that energy. When it melts and become water, it had to change to water at 10 degrees. So it's undergoing 2 changes, and we have to find it separately, E1 and E2. What's the formula we're going to use in E1, Malachi? Yeah, during the melting phase. What's the formula we're using? Only have 2 formulas. Only have 2 that we could use here. Which one? Right, E is equal to ML. That's what I mean, the formula. What's the next one? I'm giving you a second chance. For the second phase, what's the formula you're using? is equal to what? Huh? FLM? What's that? ML V now, it didn't vaporize. Temperature change, what's the formula? Okay, come on, people, please. Wait. Bring it from us. I'll keep it. E is equal to MC delta theta. Because you see, in the second phase here, was there any temperature change? I mean, any phase change? No temperature change. So therefore, we cannot use this formula, right? For the second part, I mean. So we have to use this formula here. Temperature change formula. Okay? So basically, there are two formulas that we're looking at today. Latent heat formula, change of phase formula, and change of temperature formula. When it undergo a phase change, use ML. When it undergoes a temperature change, MC delta theta. So you're looking for one of those. Huh? Copy it down. Try and work it out now. Karina, you're working it out. Sorry, Kieran. Kieran, right? Yeah. Kieran. Try this, please. Let's see what you get. I give you your values there. Ten to the power 5 here. Come a little closer so you can see. So the mass is 10 grams. We had to convert that 10 grams. So that's 10 over 1000. LF. LF is 3.3 by 10 to the 5. Then we add in that to, again, we had to convert the mass. So that's 10 divided by 1000 is 0.01. C is 4.2 by 10 to the 3. And what's the temperature change that the water underwent? Grace, what's the temperature change that the water underwent? Look at the first temperature of water and look at the final temperature of water. 10 degrees, here we go. 10 degrees, right? You can work out there. I don't have much space, so I'll just write the answer here, right? On top. Work it out, please. Anybody confused? Anybody confused? Huh? Bring yours up. So you can put it in just like how I have it, right? 10 over 1000 multiply by 3.3 by 10 to the right, 3.3 by 10. Then bring the subtract and put it by, right? That'll be the first value. And you add in that to next value. 0.01 multiplied by 4.2 exponent 3 multiplied by 3. Okay, then check it back, right? Check the whole thing. Tell me what you all get.
So I'm putting it by 10, and then the 5, and floating 5. So
Yeah.
you don't press this and put the 5.
No. You just press this and you press 5.
Okay, okay.
Right? Try it on, see now. I got 3720 joules. Right? Jaden, check it back from now. Check back your work here. I got 3720. Malachi. I will take it. Time to do the work again. You can use your phone. Piece by piece, yeah.
Right.
Sharon, check it back again. I seen a mistake. It's supposed to get 3720. Why are they walking around all over class? Yeah, you have a Casio just to put the bracket. See, then if we fix it there. Kieran, you getting it? You have a calculator? You have a calculator? You get it? So you can do it because you have a sharp, you do it part by part, right? So you can put 10 divided by 1000, right? And then you multiply that by 3.3 and you press EXP, right? And then you put 5. By the first part, right? Then you add it to the next part. 0.01 multiplied by 4.2 exponent 3 by 10. Those brackets. Right? I'm trying to say using EXP, right? To get it 10 to the power. All right, let's go again. Let's go again. I'm going to push you into a past paper type question now. Any questions there online? Kiran, are you there? Ishana again. Sure, I didn't get your answer. Did I? Kiran, Ramlal. Right, remember the whole thing, Faraj. I see some part of it there, but the whole thing, right? So E1 was how much? 300. Yeah, and the second part was 420, right? Kiran? Barrage, so you got the second part right. The first part is 3,300, you have to add them together. Kiran, are you there? All right, who is Kiran Ram? All right, let's try our next one here. All right, this one here had two parts. I will show you both parts, right? But I will stay on this slide, right? Just do me a favor now, please. This has two parts. Write this down now. Heat energy to convert all of ice at 0 to water at 0. And then I will turn back to the values. Write this down, please. Heat energy required, all of ice at 0 to water at 0. Ice at 0 to water at 0. Okay? It has two parts now. So I don't want to flick between them. Heat energy required to convert all the ice at 0 degrees to water at 0 degrees. All right, I'm going back to all the values, right? So do part 1 and then do this part for me. But the part 1 has all the values, right? Go ahead, try this, please. Take your time, right? Find the energy, use the right formula, and then let's see how this works out, right? So you have part 1 and 2 to do, huh? Right, so again, in this topic, all you have to figure out is if it's undergoing a temperature change, phase change, or both. Right, so in this first case here, what you all think happening here? It's staying ice, right? And it's going from -10 degrees ice to 0 degrees ice. So is that a phase change or temperature change? Yes, sir? Temperature change, nice. So the formula for temperature change is what? E is equal to MC delta theta. What's the mass of the ice? 2.5. What's the temperature change the ice underwent? Sorry, what's the specific heat capacity of ice? 2.1 by 10 to the 3. And what's the temperature change the ice underwent? 10 degrees, right? That's okay? How much is that? 52. 52,500. Right, 52,500. All right, nice. Y'all got that? Some people didn't message except for Killia. Y'all got that for the first part? Kiran, sorry. Sahara, y'all got that there? Do the second part now and message your answers, please. Okay, please remember to message your answers, right? Do the second part, right? For those who didn't get, this is the second part. Heat energy required to convert all the ice at 0 to water at 0. Heat energy required to convert ice from 0 to water at 0. All right, and just turning back to the values, right? Right, so use the right formula, message your answers. Huh? We're done. Can we just do that? That's 52,500. We're doing part 2 now. And you got that? You didn't get that? Oh, why you did part 2 alone? Oh, okay, well, do it now. I'll tell you the answer after. I'll tell you the wrong thing that's now. 0 degrees ice to 0 degree water. Oh, yeah. Work it out, message your answers. Huh? No, we can. Yeah. I know. I gotta stay on hold night. I'll take a break. I'm with that. Check it and see if you are to believe me. Now okay. In front of your hot room. I share a lot. Right, work it out, message your answers online. What's the formula we using? Let me see who I'm Kiran. What's the formula I think we're using here? Very good. No temperature change. So what's the formula we're going to use? So there's no temperature change, right? So what's the formula we're using here? Kiran? Right, Kieran, it's just two formulas we're using today, right? E is equal to MC delta theta when there's a temperature change. And E is equal to MLF when there's a phase change. All right. So which one do you think we're using for this part 2? MC delta theta, MLF. Thank you. Thank you, Kieran. 52,500. You multiply by 10 after. So the mass is 2.5. LF is latent heat of fusion of ice is 3.3 by 10 to the 5. MC delta theta, temperature change. In part 1, there's a temperature change. In part 2, there's a phase change. So you have to figure out which is which, right? And when to use it. Right, I got 825,000 joules. Right, good job, Kieran, Karina, those who send the answers, good. Shannon, good job. Katrina, why you multiply by Katrina? I feel like what you're wrong one, Katrina. Remember, it's the latent heat of fusion of ice, right? Sorry, mistake. Right, yeah. Remember, you only use heat capacity whenever there's a phase change. I mean, a temperature change, right? All right. Let's see if we can squeeze in one more now. One more of Kahoot and we're done. Again, one little Kahoot here. Right, this one is May 2019. May 2019. Number 3C. Hold on, I'll share this one. Why can't come here? I was turning around way. Wait, I was turning around before. But distracted, you know. I hope you all can see it. That's not the best one. And the page kind of curved. If you want to download, if you want to get the paper, it's May 2019, number 3C. Huh? 825,000. Right, try this one now, please. Right. I'll have to move in and out, right? Because you'll need, all right, here what to do. Write down these two values here because you'll need them. Write down those two values. Latent specific capacity of water and latent heat of vaporization of water. Oh, you have to figure it out which one you're using. There's one on the next, right? I take this off. Huh? I'm telling you, check it and see it now. Right, heat capacity is that and latent heat is that, right? Okay, go ahead. Try this fast, We're trying to get cast it up. Come on, sit down in front. Hurry up, try this one earlier. Last one. It still have a third part, yeah? It still have a third part. I mean, part 1 and 2. I just gave it. I just gave it the values just now. These are the values that we'll need down here. Heat capacity of water, specific capacity of water, and later on theta vaporization. All right, hurry up. Let's see if we get this. You get it now? 2.3 by 10 to the 6 and 0.200. All right, go ahead. Do part 1 and 2, and then you have a next part to do, right? It's ready. Water from 50 to 100. It's 2.5 or 1? It's 1.5. They get 2.5. You do part 3 first?
No, it's supposed to be part one. Let's get that right.
They get 10. What's the temperature change of the water on the one? You thought one again.
Oh, so that's 50 degrees, so that's 100.
So what the temperature changes?
After some. Then you put up this.
Well, I can see it. I can see. Huh? Finish those two parts. I'm just moving down to the third part.
Yeah.
I will get them out just now. All right, so it should be done. Let's check it out. Seeing some values coming in, keep sending them. Who am I missing there? Didn't get from Shannon. Shannon, send yours. Parad, send yours. All right, Katrina. I just finishing this question here. Right, so part one, temperature change. So E is equal to MC delta theta. The mass is 1.5, and I could use kilograms because the final value of 4,200 is in kilograms. And temperature change is 100 minus 30. Right, so that's 1.5 by 4,200 by 70. What's that? Oh, yeah. 441,000 joules. Nice. Right. Next part. Next part, it stayed 100, but it changed from water to steam. So we should identify that that is a phase change, right? MLV. MLV. So that's 1.5 by LV is how much again? 1 point how much? 2.3. 2.3 by 10 to the 6. No, 2.3, that's the value I gave that you have there. So that's 1.5 by 2.3 by 10 to the power 6. I have what, 3 million? Joules, right? That's part 1 and 2. And last part, you want to heat water from 30 degrees to 100 steam. How are you doing that? That's just one mark. Any ideas? Any ideas how we going from 30 degrees water to 100 degrees steam? Add both, yeah. Right, Kalia said to add both values, right? Because remember, we went from 30 degrees steam to 100 degrees, sorry, 30 degrees water to 100 degrees water. And then we heat the water and we got steam. So part one, we went from here, that's part one. And then part two, we went from water to steam. So we basically did this question in two parts. So the final answer here will be the 441000 plus 3.45 by 10 to the 6. So when you add that, 441000. Right, I have 3.891 by 10 to the 6. Anybody got that? Talma?
Yeah.
So it's gonna be 44, right?
E, energy.
LFE.
Here? No, I just draw arrow. That's just the energy.
Just making sure the answer is 3891000.
Yeah, 3891 and 3 zeros. Trouble? All they asked in part 3 was to basically add up part 1 and 2. Right? Some questions they break it up here, some questions they ask and you have to figure it out. Okay? All right, sad news. I don't have time to do the Kahoot.
Yeah.
It's a long one.
10 to the power of what?
10 to the power 6. Huh?
We are live that we could move it around. So just making sure 3.8 by 10 because
3.89 by 10 to the 6. 3.89 by 10 to the 6 too.
like please what is it?
All right. Let's see how far we can reach.
Now we move it.
Log in quick. If we take long to log in, we'll stop. All right, so log in quick. We mightn't get to the whole thing, but I will see. Log in quick is on thermal only.
No.
Log in quick, come out closer because you might be able to see some of the thing. You are log in already. Hurry up, log in quick. All right, time up. Let's start. Yo, me to relax. I want me to relax. See? Hurry up now, moving slow. On that press beat all you
Hey,
by one.
I talk about you on that 15 game and encourage them to I don't have run.
Wait, when is all the marathon Ricardo? And when is sports day? When is sports day? That was sports day?
Yeah.
Also, what I had today?
Oh.
All right, let's go. Anybody else? Not working? Answer. Wait, who's answer? Who's answer? What is serious? Try one more time quick. Right, we won't get to do all questions, but I will do the shorter ones. Again? All right, let's go. Start quick. Lagging? Hey, wala team thing na, no? Well doing. No, no, no. Shannon, you get that wrong? No, 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 no. Let's do real bad in this. I feel I want to give us some time to go over this, huh? Wait, wait, wait. I'm gonna see. One person get that right. That was Leah. I'm giving you one, but I'm gonna see how y'all doing this one here. It's the easiest one to top. The people getting this wrong. All right, let me skip the one that should be fresh in your Malachi. Everybody get anything wrong, you shouldn't be happy. That's not. I'm gonna skip up. Actually, this one easy. This one easy. All right, thank God we get that one right. Good. I'm gonna take that. Who on top now? Katrina on top. You know, again, back the same thing next. Perfect.
Then get made up time to answer.
Are we getting a few more right? Let me see any change here. Is Shana, Leah. Who's Leah? Leah. Good. Watch. Should get this one right. Come on, let me get all right in this for this one. Let me try to get all right here. Amen. That's a little better. Who get it wrong, Malachi? You? Jacob. I'll see that's now, don't worry. Look, well, Jacob get it right. True or false? Nah, man. I sure that I get all these right. Jose, electric nuclear here, man. Quick calculation here. Can I calculate this out fast? Find the energy fast. Nah, what y'all do? Oh, y'all probably put it wrong units. Okay.
是 that's it go
Oh,
ING 这种
well, you have to remember to do that.
也大一些
Huh? You have to do that. And we now do that, you know.
yeah again everybody school
You do one big bit.
yes sir
3 more. 3 more and we done.
yeah I thought wrong
Look how easy one here. You get a chance to get some right.
you talk to I said是 and every single this
All right, now but better than the others. Katrina and Cameron close. That's the closest. Double points, so probably a calculation, right? Hurry up. Woo, this one hard.
you need my more
200 watts, a 200 watt heater is on for 2 minutes. That's like a lab with it. Liquid of mass 3 kilograms.
oh
Right, so that you'll get that wrong anyway. And I'm not telling you the right thing because I'm gonna give you back this next week. Last one, true or false?
this
Some more, let's guess. We did this last week. All right, please for homework, revise thermal. All right, let's see. Cameron third, nice. Wait, look at them scores all here, real bad. Leah and Katrina. Wait, who was Leah? Leah. Oh, Kalia. Okay. All right. So please do some revision when Katrina passed, right? When Katrina passed. So we have some revision to do. You're getting this plus more calculations, right? I'll add on some more. All right. So no class Saturday for those who come to that class, right? All right, online. That's it for today. We have class on Wednesday, Thursday, Friday. No class Monday and Tuesday. Okay, so that's it online for today. You all can log out.